So all we're going to do here is we're going to look at a few techniques that are often useful in solving problems involving probability that we may not have encountered thus far in Unit 1. So we're going to do three questions here. One of them is going to involve taking groups, grouping things within a group that we are making. The next one is how many ways you can arrange things if you're putting them in a circle, which is slightly different kind of arranging. And the third one is a topic we've encountered already, but you're going to get a lot of practice using in this course, figuring out probabilities or a number of arrangements using indirect reasoning. So let's look at our first problem here. How many ways can you arrange the letters in the word question if all of the vowels must be together? So it's a permutation type question, but we've got things that specifically we have to keep together in the question. And the way to do this is to think of these vowels as a single letter. Okay? We've got to keep them all together. So when we're counting up how many letters we have, think of the vowels as a single letter. Okay, so we've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 letters. Okay, how many vowels do we have? Well, we've got 1, 2, 3, 4 vowels. Okay. So let's pretend that all of these vowels are one sort of letter or one thing to arrange. So if we take out those 4 vowels, we have 4 consonants, and then we add that sort of all of those vowels together, so we've got 5 letters to arrange. Okay. So how many ways can we arrange our 5 things? Well, if we have 5 things and we want to arrange them, the number of arrangements is going to be 5 factorial. Now, how many ways can we arrange these 4 vowels inside this single letter? Well, we've got 4 vowels. How many ways can we arrange them? We can arrange them 4 factorial ways. So let's say this is us arranging vowels within the letter or within their little subgroup. So we can arrange the vowels 4 factorial ways. We can arrange everything else, including this group of vowels, the 5 factorial ways. So our total number of arrangements is going to be 5 factorial times 4 factorial. Okay? What is this going to equal here? Who's got a calculator? Who can calculate this quickly? 5 factorial times 4 factorial. $2,880. Anybody else get that? All right, awesome. Okay. Now, our next question was, how many different ways can you arrange the letters A, B, C, D in a circle? Okay. Now, what we've been thinking up until now is we've got them in a line there. If we were arranging them in a line, it would be our standard, well, we've got 4 things. So we do our permutation. We could arrange them 4 factorial ways. But if we're arranging them in a circle, things are a little bit different. We can think of arranging them kind of like A, B, C, D, okay, around a circle kind of like this. Or I could arrange it, I don't know, so maybe something like B, A, B, C, around a circle like this. The problem is these 2 arrangements are actually exactly the same. all I've done here is I've rotated it kind of around like this. Okay? So we end up with, and we can imagine rotating it again, C, D, A, B is another circular arrangement, which is again exactly the same. B is still in between C and A, C is still in between B and D, and so on. And if I turn it one more time, I get B, C, D, A, kind of like that. So we've got 4 arrangements here that are actually identical to each other. So let's just say, but many of these arrangements are the same. Okay. So in fact, for any one arrangement, we get 4 arrangements that are, 3 other arrangements, or 4 in total, that are exactly the same. Many arrangements are the same. Let's say 4 for each arrangement. So every time we make an arrangement, it turns out that 3 other ones in the list are exactly the same as that. So how do we figure out how many unique arrangements we have? Well, similar to when we were working with indistinguishable elements. The total possible arrangements are 4 factorial. For each arrangement, we have 4 that are the same, so we divide out those identical arrangements. So we'll end up with 4 factorial, which is 4 times 3 times 2 times 1, divided by 4. Or just 3 factorial, which in this case gives us 6. Okay? So, in general, did I put this on the next page? Nope. So I'll just write it down here on the bottom. In general, if we have a circular arrangement, there are n minus 1 factorial, so the number of elements minus 1 distinct arrangements. So let's use that to solve our final problem here. How many ways can King Arthur and 12 of his knights sit at the round table? Okay, so how many people are we trying to put at this table? 13 people. Okay. So how many arrangements are going to be possible? We're putting them in a circle, so it's going to be n minus 1 factorial. So in this case, that's 13 minus 1 factorial, or 12 factorial, different ways. Now, we could work out what 12 factorial actually is, but it's, well, it's a big enough number that it's probably more compact just to say 12 factorial in this case. It's actually 479 million and a little bit. Okay, so we'll just leave it at 12 factorial. Now, what if we add a little twist to the problem? King Arthur and Lancelot, one of the knights, refuse to sit next to each other. Now how many ways can we arrange these 13 people? Okay. So this is kind of indirect reasoning, okay? We can't calculate, it's hard to calculate directly how many ways we can arrange these things. But what we can do is we can figure out if we want to figure out the number of ways we can arrange them, it's going to be the total number of ways we could arrange these 13 people without restrictions, or without this restriction that Lancelot and Arthur can't sit next to each other. Okay. Okay. And then we're going to take off the number of ways that we can arrange King Arthur, and I'll just call him Lance, can be together. Okay? So the total number of arrangements minus the number of arrangements that have King Arthur and Lancelot together. Okay? Because if we take away all the ones where they're together, we're left with the number of ways that we can seat everybody so that they are apart. So we know the total number of ways without this restriction. That's 12 factorial. We did that up at the beginning. How many ways can King Arthur and Lancelot sit together? Well, again, just like when we were working with those vowels, let's treat Arthur and Lancelot as a little unit, okay? Treat them as one person for the time being. So if they are one person, we now have 11 factorial ways that we can arrange all of these things, okay, because we've taken two people and combined them into one. And then how many ways can we arrange Arthur and Lancelot inside their tiny little group? Well, there's only two of them, so 2 factorial. So this is with Ka and Lance, I'll just shorten it down to L, as 1, okay? And then this is the number of ways that we can arrange just Ka and L. And now we just work it out. So it's going to be 12 factorial minus 2 times 11 factorial. Whoops, that's just a 1 factorial. We want it to be an 11 factorial. And I did it again. Okay. So what is this going to equal? 12 factorial minus 2 times 11 factorial. Who's got a calculator? It's going to be still a big number. 399, is that millions, thousands, or just 399? And that's it. So it's still a lot of different ways. Okay.